All right, so in 3.8, we are going to be doing our final way to solve systems of equations. We're going to be doing that using inverse matrices. So in this first half, in the 3.8a video, we're going to be learning how to find those inverse matrices, and then we're going to learn how to use them to solve systems of equations. So first thing is the identity matrix. The identity matrix, first of all, it's a square matrix. It's got to be a square matrix. And square matrices are literally squares. They have the same number of rows as columns, so a 2 by 2 or a 3 by 3. And it's a square matrix that if you multiply it by another matrix, you get that same matrix back. So basically what you see is a matrix with ones on the diagonals and zeros everywhere else. So 3 by 3, it'd be like 1, 0, 0, 0, 1, 0, 0, 0, 1, etc. So we could do the same thing with a 4 by 4 or a 5 by 5. We just won't be using anything beyond a 2 by 2 and a 3 by 3. So again, the important features are that the diagonal from left to right are ones and everything else is 0. So same thing here. And again, the 4 by 4 and beyond would be the same. An inverse matrix. Two n by n matrices, we say they're inverses of each other if their product is the identity matrix. So let's say matrices are inverses if their product is the identity matrix. Two matrices are inverses of each other if their product is the identity matrix. So think of like inverses of numbers. Like we said that 4 and 1/4 were inverses of each other because when you multiply them together you get 1. 1 is the identity number. So for example, we would say that A times A inverse, that's just that notation we use for an inverse matrix, equals I, and we use I for the identity matrix. So the identity matrix, anytime you see a capital I, it's talking about the identity matrix. And then anytime you see A with that little inverse, that -1 superscript, that's the inverse matrix. So it could be a B inverse, C inverse, etc. It's more that little superscript that means we're talking about an inverse matrix. So for example 1, first we're going to determine whether they're inverses of each other. So when we multiply one by the other, we should get the identity. So when we multiply them together, we have, so x by y, so multiply 3 times -2, -1, 1, multiply that whole thing by 1, 2, 1, 3. So this is the flashback to 3, 6, multiplying matrices together. So since this is a 2 by 2 and this is a 2 by 2, we know our answer is going to be a 2 by 2. Leave some space for the adding and multiplying. So this spot right here is row 1, column 1. So we're going to use row 1 here, column 1 here. Multiply 3 times 1, we get 3, plus -2 times 1, we get -2. Next, move to row 1, column 2. So multiply these together. 3 times 2 is 6, plus -2 times 3 is -6. Down here, row 2, column 1, so row 2, column 1, -1 times 1 is -1, plus 1 times 1 is 1. And last spot, this is the second row, second column, so -1 times 2 is -2, plus 1 times 3 is 3. So combine these all up. In the first spot, we have 3 and -2, that's 1. 6 and -6 is 0. -1 and 1 is 0. And -2 and 3 is 1. So see how I multiplied them together and I ended up with the identity matrix, which we have right here. And so that means, yes, they are inverses of each other. Okay, let's do the same thing with part B. We're going to multiply P times Q. Okay, so again, since these are both 2 by 2 matrices, I know when I multiply them together, I'm going to get another 2 by 2. So start with row 1, column 1. So row 1, column 1. 3 times 1 is 3. -1 times 2 is -2. Move over to row 1, column 2. 3 times -3 is -9. -1 times 4 is -4. Move down here, now I'm in the second row, back to the first column. 4 times 1 is 4. Negative 2 times positive 2 is negative 4. And finally, second row, second column. 4 times negative 3 is negative 12. And negative 2 times 4 is negative 8. Okay, so combine these up. 3 minus 2 is 1. And then this gives me a negative 13. So I know as of this point that they're not inverses of each other. But finish it off. We got 0 and negative 20. So this is definitely not the identity matrix, which means that no, these ones are not inverses of each other. Okay, so what we're going to do with the rest of these notes is actually talk about how to find the inverse of a matrix. So in this top half, we figured out how to see like if they're inverses of each other. And like I said, we're going to figure out how something, how you can find the inverse of something. So the inverse, it's got a formula. So A inverse. So let's start off by writing what I mean when I write down A. So we've got A, B, C, D. So A inverse starts off like this. We do 1 over the determinant, which is A times D minus B times C. And then in here I have D, negative B, negative C, A. Okay, so just to point a couple things out that might make things easier for you to remember, this denominator right here is the determinant of A. Remember we put that in those bars, that represents the determinant. So that's the same formula that you guys used in the last section in 3-7. And now notice on this diagonal, so this diagonal right here, I swapped those two. I swapped A and D to give this diagonal, and then in this diagonal right here, I made them opposite. Okay, so that's just a little something to help you remember. So 1 over the determinant, you swap this diagonal and make this diagonal opposite. All right, so let's go through, find this matrix, and then if it exists, so if AD minus BC equals 0, no inverse exists. So that could pop up at any time. So just know that that's true. If the denominator would be 0, you'd have 1 over 0. That's undefined. So if that happens, that means that there is no inverse. So B inverse. Let's start with 1 over the determinant of B. So I cross multiply here. Negative 1 times negative 2. And then minus, cross multiply here. 0 times 8. And then I multiply this by this new matrix. So remember this diagonal right here, I'm going to swap them. So the negative 2 will go up here, and the negative 1 will go down here. And then this diagonal, I make it negative. So negative 0 is still 0. This will swap to a negative 8. All right, so I end up with 1 over, this of course is 0, but I have negative 1 times 2, which is negative 2. And then this new matrix. So this goes back to section 3.5 where I multiply by a scalar. So all I'm going to do is distribute this negative 1/2. So negative 1/2 times negative 2 leaves me with 1 in that first spot. Times 0 is still 0. Negative 1/2, whoops, I jumped the gun here. Sorry, that's an 8. I already cut it in half. 1 over negative 2, and then times negative 8 would be a positive 4. And then negative 1/2 times negative 1 would be a positive 1/2 in that last spot. So this is the inverse of matrix B. All right, we got one more here. Okay, so then T, so I do T inverse would be 1 over the determinant. So cross multiply here. Negative 4 times positive 3 is negative 12. Minus, and then cross multiply here. 6 times negative 2 is negative 12. And then set this up, so this diagonal I swap, 3 and negative 4, and then this diagonal I make opposite, so negative 6 here, positive 2 here. So we simplify down, negative 12, this changes to plus a positive, and if you look right here, I've got 0 in the denominator. So that automatically means that no inverse exists. So you may have noticed that that denominator was going to be 0 before I even set this up. If you did, you can just right away say that no inverse exists. All right, so in the next video, we're going to learn how to use these inverses to solve equations.